welcome to Engineering Tomorrow's session on green hydrogen and decarbonization. My name is Eric Einset. I'm a chemical engineer, and I've been working for over 30 years in various industries. And one of the industries that I'm working on these days is actually renewable energy and really the energy transition in general. And we're going to talk about what that is all about. So let's get started with green hydrogen and decarbonization. As you know, or you may know, all of our labs are developed here at Engineering Tomorrow by engineers and engineering students. So this lab was developed by me together with Grace and Allie, who are currently students at students in engineering. And they spent a lot of time putting this together, and hopefully you'll enjoy the lab and get something good out of it. So first of all, let's talk about what is decarbonization. So decarbonization is essentially taking the sources of carbon dioxide or any other gas that acts like carbon dioxide that is being emitted into the atmosphere, and to try to reduce those sources and try to reduce the level of carbon dioxide or equivalents in the atmosphere. Now, these other impactful gases are often called greenhouse gases, or GHG. And the reason they're called greenhouse gases is because they really make the atmosphere behave like a greenhouse. So what's happening on Earth is that the sun's radiation is coming through the atmosphere, warming the Earth. And normally there would be cooling also, through conduction and convection, and radiation away from the Earth. But as the atmosphere is changing, these greenhouse gases are inhibiting the cooling of the atmosphere or cooling of the Earth, and that is causing general warming of the Earth. So you might ask, how do we know that this is true? Probably one of the best measures of the carbonization of our atmosphere, if you will, is to look at carbon dioxide levels over a long period of time. Now, in this next few slides, I'm going to show you a number of graphs, and this is how engineers convey information, how they can take complicated data, put them into a story, to make it understandable for people. So what you can see here on the left side is a graph, just an XY graph, of time on the x-axis, and this is 400,000 years, and then the carbon dioxide level in the atmosphere. And as you can see, the carbon dioxide level does go through broad climate cycles, which is natural processes of Earth. But if you look in the very far right-hand side of that graph, you'll see that the carbon dioxide level is starting to really spike. And you can see that the scale is very, very large. And what we want to do is zoom in on that, the more recent years. So that's what the graph on the right shows. This is now a graph with two y-axes, and it's plotting two different things. The pink line shows the more recent increase in CO2 in the atmosphere. We're approaching, we've exceeded 400 parts per million now on average. And the axis on the other side, the blue line, shows the actual emission of carbon dioxide through the last several hundred years as the world has been industrializing. So as you can see, they seem to be following the same general trend. As you can see, starting in around the mid-1800s, the Industrial Revolution occurred. We started to see a lot more CO2 emissions from industry. And what seems to be happening is that following that is an increase in the level of CO2 measured in the atmosphere. Now, this is likely a major factor, highly likely a factor that's driving changes in our climate. It's been in the news, all the time. You're seeing news articles about severe storms, severe rainfall causing flooding, severe heat, long periods of very, very high temperatures. And ultimately, this is also going to be driving rising sea levels and a lot of changes. And frankly, there's not really an understanding of what is going to happen, but we do know that things are changing. So decarbonization is trying to reverse this. So we might ask, where is all this CO2 coming from? And also the greenhouse gases coming from? So this is a Pareto chart. It's a bar chart that also called a Pareto chart because it lists the major drivers in order of their importance. And as you can see, China is actually one of the largest emitters today of greenhouse gases. Now, that's not surprising. China has gone through a tremendous growth in their economy. They've created a lot of, millions and millions of middle-class citizens who want to drive cars. They want to buy houses. They need more electricity to have a good quality of life. And what's happening is that's driving a lot of increase in their emissions. Now, the irony is that China is also, even though they're largest emitter, they're also the largest producer of clean energy. They're building a lot of wind farms and solar farms, so they're trying to offset this. But the problem is they're also building coal plants and other polluting sources just as fast or faster. Now, another part of this chart I just want to mention is on the right-hand side, there's a thing called the Kyoto gases. So this is actually a list of some of the greenhouse gases. And the way they're measured of their impact is in relation to the equivalent of carbon dioxide. So a pound of carbon dioxide, the way to interpret this is that a pound of methane is basically 25 times the impact of a pound of carbon dioxide. A pound of nitrous oxide, which is actually something that gets emitted in farming and agriculture, is almost 300 times. And then if you look at some of the other compounds that are on that table, a lot of these fluoride-based compounds are extremely severe when it comes to global warming impact. So what this is, the picture that this is telling you, this graph is telling you, and that information is telling you, is that the big drivers of greenhouse gas emissions is China, and then the U.S. and Europe and India, and then you can see the other countries, and that it's not just carbon dioxide, but also other compounds that are having an impact. The next question is where does the CO2 or the greenhouse gases come from? On the previous page, we looked at which countries are the major emitters of greenhouse gases. In this plot, we look at what industries play a role in emitting greenhouse gases, and this is a pie chart, and it shows out of the full 100% of greenhouse gas emissions, what fraction goes to each industry. So you can see that electricity, so the electricity in our houses and the grid, plays about 26% of the greenhouse gases come from that. For transportation, so cars and trucks and ships and airplanes, about 16% comes from that. In agriculture and the use of land and landfills, about 21% of the greenhouse gas emissions comes from that. And then what we'll do is we'll talk more about in industry what sources are. So the question is, what can we do about all this? And the fact is, we're already doing a lot. The world is already working hard to replace fossil fuel-based electricity generation with renewables, so things like wind and solar energy. On the transportation side, the increase in the use of electric cars is a positive impact. So it's as long as those electric cars are being recharged with renewable energy, that has a net reduction of CO2 emissions or greenhouse gas emissions. There's also a lot of work trying to develop sustainable fuels, which can be used in aircraft and in large ships to reduce the impact of greenhouse gases. And also buildings, like instead of using a propane or natural gas furnace to heat your house, using more heat pumps and things like that can help. So a lot is happening. And all these topics, all these things, kind of all come under the category of an energy transition. So the energy transition is a major activity in the world today that is happening to try to move ourselves away from carbon-based greenhouse gas emissions to an industry and a world where it is more renewable, and there's a reduction in the CO2 or greenhouse gas emissions, so that we can hopefully drive down the CO2 effective concentrations in the atmosphere and reduce the impact of climate change. So let's talk a little bit about the industrial sources of greenhouse gases. The issue is that there's no real simple solution. And this was one of the biggest contributors to greenhouse gas emissions. but it's also very varied. You can see that in the production of iron and steel and chemicals and cement. All these things are fundamental to our lives, our infrastructure. They all have some contribution to greenhouse gases, whether it's the reactions to reduce iron ore in the iron and steel industry, or if it's when they produce oil and gas or coal. There's fugitive gases, methane released from coal. There's flaring of natural gas quite often in the oil industry. Another area is in the chemicals, in the production of ammonia and fertilizers. There's a lot of hydrogen used in refining. So what kind of is a common theme in many of these? It's not a complete solution, but a common theme is that hydrogen is used a lot. And the question you might ask is, why is hydrogen a problem? It turns out the traditional production of hydrogen produces CO2. So when I talk about the traditional production, it's essentially production of hydrogen with methane as a source. So let's look at what that looks like. So today, most hydrogen is produced with CO2 as a byproduct. So this happens in what's called a steam reforming and water gas shift reaction, which is shown on the left-hand side here. So the overall reaction is that you start with CH4 or methane, which typically is coming from drilling and from under the ground. That's reacted with water to produce CO2 and hydrogen. So the bottom line is that for every pound of hydrogen you produce about 22 pounds of CO2. Now, there are a couple of things that you can do. If you take and undergo this reaction and then release the CO2, that hydrogen you produced is usually called gray hydrogen. And you'll find that there's a whole nomenclature around hydrogen. But gray hydrogen is essentially the steam reformed water gas shift reaction with CO2 going to the atmosphere. Now, you have an option that you can take that CO2 and you can capture it. And there's a process called carbon capture, where you take and you capture the CO2 and then you bury it. You basically put it back in the ground and it's not released to the atmosphere. So that's better. And any hydrogen produced that way is actually called blue hydrogen. So, but in the end, both of these are producing CO2. And of course, as you may have remembered for the previous slide, the production of methane from the ground also has its own carbon emission issues. So there is another way of producing hydrogen, and that's through a process called electrolysis. And what electrolysis does is essentially takes the hydrogen and oxygen in water and breaks the water down to produce hydrogen gas and oxygen gas. So what you need to do this is obviously water, and you need electricity because this electrolysis process is being done in an electrical cell and is driven by electricity. So if you can drive this with clean electricity that's made from in renewable sources, then you'll produce hydrogen that is actually called green hydrogen. So the process is that you have renewable electricity driving in an electrolysis cell, the process to produce hydrogen and oxygen. And then for every pound of hydrogen you produce no CO2. Now, this is a chemical reaction, but to do this on scale, you need to build a plant. So this is a picture of what the hydrogen electrolysis, green hydrogen electrolysis plant can look like. So as I said, every pound of hydrogen produces no CO2, which is a benefit. Now, this green hydrogen now can be used in a lot of places. It can be used in fertilizer production. It can be used for reducing, iron, for steel production. It can be used in a lot of things. It also can be burned. Hydrogen actually is flammable. It's a fuel. And there are a lot of sources or a lot of applications for hydrogen. So the idea is that you have something that looks a little bit like this. This is kind of a process flow or a flow of electricity, if you will. If you look up in the upper left, you can see we start with generation of electricity from wind and solar and geothermal sources, so renewable power. That renewable power can go to your house to heat your house. It can be used for heat as a heat pump to warm your house. It can be used to charge up electric vehicles, and it can be used just for general conventional uses. Part of the electricity can then go to the electrolysis process, and together with water, it can be used to make green hydrogen. And then the green hydrogen can be used in the chemical industry to make fertilizer and other chemicals. It can be used in the synthesis of chemical fuels, and those chemical fuels then can be used for heavy transport. One example of that is something called SAF, Sustainable Aviation Fuel, which is basically a fuel that's used for aviation, for aircraft. So this is all very nice picture. This is the kind of the nirvana of the use of green hydrogen, but there is a problem, or there is a challenge involved here, because all these steps in the process, in order for them to actually happen, they have to be economical. So this is one of the big challenges of engineering, of society, of governments, is to figure out, first of all, can this become economical? And it has to be economical for this to have an impact on the total decarbonization. What you're going to do now, we're going to talk about what your lab is about. You're going to actually produce green hydrogen. And it's actually remarkably simple to do. So what you're going to do is you're going to have just a few things. We need you to start with a plastic water bottle. You don't need the water in it. You can drink the water if you've got a full water bottle. What you're going to do is you're going to cut it in two so that you have a little pool that you can put water in. We're going to use a straw, a battery, or you can use a solar cell. We'll be providing a battery. And then you're going to use 2 pencils as your electrodes. We'll talk about this a little bit. And then, of course, a jumper wire. So your task is to build an electrolytic cell and capture green hydrogen. The basic design you can see in the picture here with the battery and the 2 pencils in the water. And then what I've shown on the right is a picture of the cell that I made. But what you can see is the leads of the battery connected to the pencils. And they're going to then be, as the charge is going through and the circuit is completing, you're actually going to be producing hydrogen and oxygen. So let me just show you, before I show you a little bit more detail about assembling this and the importance of each element here, let's look at the actual reactions involved. So this is essentially the splitting of water, or the electrolysis process. As I said, you'll have a battery, and you'll have basically a current in a circuit running through the water. And so the negative terminal of the battery, you'll have electrons coming out, going through the pencil, through the lead, because the lead in the pencil is the graphite electrodes. So from the negative terminal of the battery you're going to be starting to see gas, and that'll be hydrogen gas. On the positive terminal of the battery, you'll also see gas, and that'll be oxygen gas. And if you're in a chemistry class, you can see from the slide what the actual chemical equations are. Okay, so basically, I want to show you a couple of the keys here to making sure that you're successful in this, and how to use some of the materials. As I showed you, or as I mentioned, there's just some basic things that we're going to use. So first of all, on the actual container, what I did was I took a plastic container of my own and just cut it in half. And so this is going to be my kind of water of well. I'm going to fill it up, not all the way to the top, but most of the way to the top. And then what I have is a couple of pencils. So obviously these are just basic graphite pencils, and it's the graphite which are the electrodes that we're going to be using. You need to sharpen both ends of these, because we're just going to be using the graphite, and you need to have them both exposed. This is going to go into the water, as you can see in the picture, and then you're going to attach your 2 leads, the battery, to the other ends. I've actually taped them together, but you don't have to. You can do it any way you want. And then the third thing, which is quite important, is how are you going to capture this gas? So what we have is we're going to provide you with a clear plastic straw. And what's important is that you're able to seal off one end of the straw. So what I did here, I just took a glue gun and put some glue on the inside of the straw, enough glue. I folded it over and I kind of pinched it off and held it until it dried. And what's important is that this is totally sealed, because if it's not totally sealed, any gas that you produce in here is going to just escape out the top. So you need to have it totally sealed. So what you then do is, the way you set this up is that you're going to take your sealed straw, you're going to turn it over, have the open end. You're going to pour water into the top and just fill this up with water. Then you're going to put your finger over the top, turn it over, do it that way. And then assuming there's water already in your little well here, you're going to put this in the well, release your finger, and the water should stay in the straw. So it should stay up at the top. It's not going to run out as long as this is fully sealed. So it's a good check to make sure that this is fully sealed. If you really want to verify that it's fully sealed, you might want to just let it sit for a little while. Make sure the water is not slowly draining out, because you don't want to have any air coming in the top. And then what you'll do is depending on your design, you'll put your cell, your electrodes into the water, position the negative electrode underneath your tube here, your collection tube, plug it in, and you should start to see bubbles coming off very, very slowly. It doesn't happen fast. It's very slow, but it'll eventually grow, and the bubbles will be quite small. But this is where your engineering comes into play. So how can you, that was just a very simple way of designing this and setting it up. Is there a way that you can be smarter than me, find a better way to build this? Maybe you put the pencils in through the side and seal it off with a glue gun. Maybe you could put them underneath so that they're running right into the straw. I mean, there's all kinds of ways that you can design this. So we want you to be creative and figure out what's the best way. You can also make a taller cut of your bottle. There's all kinds of things. But what you want to do is try to figure this out. Now, one other thing is to measure your generation rate, how much hydrogen you're producing. You should take the dimensions of the straw. What's the diameter? What's the cross section? And then if you can measure over time how fast the gas or the water goes down, because the gas is displacing it, that should be enough to allow you to calculate how fast you're producing hydrogen. And that would be the ultimate goal if you could figure that out. Once you've got that working, another thing you can try is to take and add some salt. It's the basic sodium chloride. Add some salt to your water. And if you do that, you're going to change the chemical reaction. And you can study this separately if you want to. But in that case, what you're going to do is you're going to be producing hydrogen, and then you're going to be producing chlorine from the other electrode. And now chlorine is actually a dangerous gas, but you're going to be producing very little of it. So I don't recommend trying to smell it, but that is basically another chemical reaction, another way of doing this. And this is actually very applicable today, because what the ideal case, most of the water in the world is in the oceans, which is a complex solution of all kinds of salts. So if we can figure out how to do the electrolysis process with salt water from the ocean, that would be very helpful. But again, it's a complicated process because the chlorine in the water also is very corrosive. So there's all kinds of engineering challenges that need to be overcome. But you can try this and see how you can change the chemistry. So the energy transition needs people with skills to design and build and operate these types of facilities. So it's not just engineers. Obviously, we need engineers, but we also need people who are trained and who are skilled in craft and trade tasks. Pipe fitters and plumbers and electricians, I&E techs. I mean, all these things are critical to being able to build these types of facilities. You also need people who can understand the process, operators to run the plant. We need chemists to test, the chemistry of things. We need technicians. We need mechanics. And there's a lot of other industries, a lot of other roles that people that are needed, skilled labor, skilled people to actually, get us through the energy transition. And these don't have to be 4-year college degrees. You can do these things in 2 years, tech training schools, apprenticeships, trade schools. There are a lot of ways of doing this. So even if you don't think engineering or if 4-year college is not your thing, there are really opportunities. If you're smart, if you're ambitious, if you're interested, if this interests you or excites you, there are ways to take part in it. Some of the questions that, or goals here and extension ideas, if you really enjoyed this lab, can you design a reactor to capture all the hydrogen produced? I mentioned this before. Don't just take my design of having the pencils lying in the water and then the straw lying on the other side. There are better ways to do it. So things to consider. Why does the water in the straw not drain out when you place it in the water? Think about how that works. What factors impact how fast you can generate your hydrogen? I mean, is the salt concentration, if you're using the sodium chloride cell, does the battery voltage matter? Does the electrical current? Does the temperature of the water matter? Think about ways that you can kind of understand the process. That's how engineering works, understanding all the factors that impact the output. If you do make the salt electrochemical cell, smell the water after it's been running for a while. What does that smell like? And why does it smell like that? What does it remind you of? Can you prove that you've generated hydrogen in your cell? It's a little bit difficult because you don't generate a lot and it's kind of just in a straw. But think about, are there ways that you could verify that you've created hydrogen? And then if you have a solar cell from one of our other labs, like renewable energy or electric vehicles, could you combine that with maybe the battery from electric vehicles to build a combination solar energy battery green hydrogen system? If you want to continue to explore beyond this lab, there are a lot of areas that you can go into. You can do research on hydrogen fuel cells, how steel and concrete is made, and how the greenhouse gases are produced in those traditional processes. What's the carbon footprint of making batteries for electric vehicles? It's likely not to be zero. So is there a way that can be improved? In farming and agriculture, is there a way to capture methane that's produced? In a landfill, when we basically landfill all of our waste, some of that waste is food waste. And that food waste actually then goes through a digestion process and creates methane. So you can do research into how that methane is actually mined out of a landfill and captured. How does carbon capture work? What are sustainable aviation fuels? Can we store renewable energy in the form of chemicals? NOx emissions or nitrous oxide emissions, where do they come in agriculture? So these are all ideas that you can expand on if this is interesting to you. So I hope you've enjoyed the lab. I hope you've gotten something out of it. I know there was a lot of graphs, but that's how engineers work. They work with data, they work with information, and a big role of an engineer is to communicate to people, what's happening. So thanks for your attention, and I hope you enjoy building your own electrochemical cell and maybe find a place where you might want to fit into the energy transition. Thanks a lot.